Good day, Math 30-1s. Today we continue our conversation about trigonometric functions and graphs, this time extending beyond 5.2's sine and cosine graphs with transformations into the tangent function. And just like we can pull values out of the unit circle for x and for y, for cos and for sine, we can also pull out y divided by x, or sine divided by cos, and what results from a sine divided by cos, or tangent value, is a bunch of outputs, a bunch of numbers, and these can be sketched. So what we're going to talk about today is what does the graph of tan of theta, or tan of x, look like, talk a little bit about what some characteristics are, and really not need to get into conversations about stretches, shifting, or flipping, and really just talk a lot about characteristics. So if we were to examine on the unit circle negative 45 degrees, and I'm choosing this intentionally, negative 45 degrees, we could say that what comes out is 1 over root 2 divided by 1 over root 2, with the y value being negative, and this would give us a negative 1. If you really wanted to, you could type into your calculator tan of negative 45 degrees, and what comes out is a negative 1. You could type in tan of 0, and 0 comes out, tan of 45, and it's a 1, and we keep getting values. Now, I started to choose numbers like 80 degrees, and some numbers come out that seem a little bit unusual. 5.7 seems like quite a large number when we're used to numbers or ratios that are between negative 1 and 1. For tangent, we're not limited to values between negative 1 and 1. As we continue to tan of 90 degrees, what we get this time is an error, or an undefined value. This is because on the unit circle, 90 degrees puts us at the top, x value is 0, y value is 1, and what is y divided by x? 1 divided by 0 is in fact undefined. So there is no answer at that location. 100 degrees, we have negative 5.7, and we keep going with some values, negative 1, 0, 1, and back to 270 we are undefined because it's 0, negative 1. Negative 1 divided by 0, undefined. Now, as we graph these values, we start to see what this graph looks like. At negative 45 degrees, we're at negative 1. At 0, 0, 45, 1. At 80 degrees, which I'll need to approximate slightly, at 80 degrees, we're all the way up to a 5.7. I am approximating that as well. At 90 degrees, it says undefined, and so what I'll do is draw a dotted line through here saying, you know what, I'm never allowed to get to this place. And we've seen this in last year's lessons in rational functions, and this is called an asymptote. After the 90 degrees, we had 100, and this put us down to a negative 5.7. At 135, we're at negative 1, 180, 0. At 225, we're at a 1. And at 270, we are back to an undefined value. And I didn't choose some 260 and 280 values to get us up to these bigger numbers, but we start to get a few values, and this feels kind of strange. Now what starts to happen is you get this shape that's connecting all these dots. It's all I've really got so far. Now what's really happening? Well, imagine if I started to say, well, this doesn't exist at 90, but there are more values beyond 90. What if I were to say tan of 85 degrees? At 85 degrees, we'd be up to 11 off this chart. What if I say tan of 86? Tan of 87? We're going to get closer and closer to 90 and see what happens. Tan of 89? 57. Tan of 89.5. Tan of 89.9. Tan of 89.99. All of a sudden we're in the 5,000s. So what's happening as we get closer and closer to this dotted line, our graph is going to shoot up so high that we can really not accurately graph it. We're off the charts. This is an asymptote where we continue infinitely towards the asymptote in the upwards direction but never actually reach it. The same in fact happens on the other side, and so we have to show this asymptotic behavior. At negative 90 degrees, we would actually have another asymptote, and we would have this shape approach it infinitely here. Approaching the next asymptote, the same thing would happen. So this is the shape of a tangent graph, and it keeps occurring every negative 90 to 90 or 90 to 270 every 180 degrees. And this is in fact the period of a tangent graph, which is different, and it is worth noting that the period is 180 degrees. So when we start to talk about characteristics of this graph, we could ask about amplitude and range and x-intercepts and y-intercepts and period, and all of a sudden things have shifted drastically. So first thing to ask, what is the range of this function? Maybe what is the max and what is the min? What is the max? It will never get to a max. What's the min? It will never have a min. So there is no max or min or amplitude that we can define. So we get to say that this graph has a range, that y is an element of the real number system. Y goes forever up, forever down, and everything in between. For our y-intercept, it looks like the only place we cross our y-axis is at y equals 0. For our x-intercept, or x-intercepts, it looks like we hit at 0, 180, 360 would be the next one, and it appears that it's every 180 degrees towards the left or the right. We can write this as a general solution where our x-intercepts are going to be when x is 180 degrees times n, where n is an integer. So we can say that every multiple of 180 in a positive direction or a negative direction will get us to an x-intercept. So this is an official visual of a tangent graph, and you can see that there are a lot of asymptotes. There are a lot of x-intercepts, and the key characteristics are based on these asymptotes and this change in concavity, we'll say. So questions that we really get asked, because we're not going to do any transformations, are a little bit more about characteristics. Questions like, how many x-intercepts are there in a domain of negative 2 pi to 10 pi? Which you might look at and say, oh, in radians it's a little bit extra tricky. Where is 10 pi? Now it is important to know that you can also do this on your calculator. So if we go to our tan of x graph, and we maybe examine this in radian mode, as this question stated, from negative 2 pi to 10 pi with a scale of, say, pi, a y min and a y max. Now we did see values of 5.7 and some bigger numbers, so I'm going to change this to, say, negative 10 to 10. So I want to see a little bit of this vertical part. Question was, how many x-intercepts were there in this domain? So I can literally look and say x-intercepts. Now I do have to be cautious because it does have square brackets around these endpoints, which means the ends of this domain are included in our solution. So I would count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I would say there are 13 x-intercepts. And this is based on a visual in our calculator. So the calculator is a good way of giving us a tan graph, especially if we're looking at bigger domains. And lastly, our last question for 5.3 is asking the graph of sine of bx, so maybe there was a period change, and tan of x have the same period. Determine the value of b that would make this possible. There's two concepts that we're connecting in this question. What is the period of the tan graph? the period is 180 degrees. We're also connecting the idea that the b value is created from 360 degrees divided by the period, which we're saying if they have the same period, the sine of bx has a 360 divided by 180 calculation to give us a b value of 2. So there's two things connecting: our understanding of sinusoidal graphs and how the b value is calculated from the period, and an understanding that the tangent graph has a period of 180 degrees. So these sort of conceptual questions are a little bit more intense because they are a rich connection between outcomes. That is the end of your tangent graph. Be sure to understand your characteristics, your period changes, and that there are some strange asymptotic shapes. Good luck.